Let us first discuss the physical properties of dihydrogen. Dihydrogen is a colorless, odorless, and tasteless gas. It is a non-poisonous gas with a vapor density of 1. Due to this, it is lighter than the air as its vapor density is 14.4. The solubility of hydrogen in water is very low. Under standard conditions, only 2 parts of dihydrogen dissolve in 100 parts of water by volume. Let us now look at the chemical properties of dihydrogen. Dihydrogen gas is chemically inert at room temperature. The chemical behavior of a diatomic molecule is determined by its bond dissociation enthalpy to a large extent. Bond dissociation enthalpy is the energy required to break a chemical bond. It is defined as the amount of energy required to break 1 mole of bonds of a gaseous molecule into fragments in gaseous state at 298 Kelvin and a pressure of 100 kilopascal. In a dihydrogen molecule, the HH bond dissociation enthalpy is very high. This because, as the size of the hydrogen atom is very small, it forms a very strong covalent bond. Thus, it requires an extremely high temperature to dissociate dihydrogen into its hydrogen atoms. For example, at 2000 Kelvin, only 0.081% of dihydrogen dissociates into hydrogen atoms. Only at a high temperature of 5000 Kelvin, we get almost 95.5% dissociation of dihydrogen molecules into its atoms. It is important to note that although a dihydrogen molecule is inert at room temperature, hydrogen atoms are very reactive. This is because they have only 1 electron in the 1s orbital, and thus they readily combine with almost all the elements to obtain a stable electronic configuration similar to that of helium. A hydrogen atom reacts either by losing 1 electron to form H-positive ions, or by gaining 1 electron to form H-negative ions, or by sharing electrons to form single covalent bonds. Let us now look at the reactions of dihydrogen. Dihydrogen gas at high temperatures reacts with highly electropositive metals such as potassium, sodium, and calcium. It combines to form their respective hydrides. In these hydrides, hydrogen exhibits an oxidation state of -1. For example, dihydrogen reacts with sodium to form sodium hydride. Similarly, hydrogen reacts with calcium to form calcium hydride. Dihydrogen burns an oxygen at high temperature in the presence of platinum as a catalyst, forming water and releasing lots of energy. Dihydrogen combines with halogens to form hydrogen halides. For example, it combines with chlorine in the presence of sunlight to form hydrogen chloride. When hydrogen is passed through boiling sulfur, it produces hydrogen sulfide. Dihydrogen reacts with nitrogen at 673 Kelvin and 200 atmospheric pressure in the presence of iron as a catalyst to form ammonia. Dihydrogen reduces metallic oxides of metals that are less reactive, such as copper oxide, lead oxide, and iron 3 oxide, into their respective metals. How does the reaction take place? The metal oxides are strongly heated in a combustion tube. When hydrogen is passed through the tube, the metallic oxides get reduced into their respective metals. Dihydrogen reacts with vegetable oils in the presence of finely divided nickel as a catalyst to give hydrogenated products such as edible fats. Because of its unique properties, like forming non-polluting products and burning in air, dihydrogen gas has many commercial uses. It is used as the rocket fuel because of its high calorific value. An oxyhydrogen blowtorch that is used for cutting and welding purposes uses dihydrogen and pure oxygen. The reaction produces temperature of up to 4000 Kelvin. Dihydrogen is also used in the synthesis of ammonia by Haber's process to manufacture nitric acid and nitrogenous fertilizers. Dihydrogen is used in the manufacture of vanaspati. Here, vegetable oils such as soybean are hydrogenated to obtain vanaspati. Commercially, it is used in the preparation of hydrogen chloride as a reducing agent to reduce metal oxides into their respective metals, and also in the manufacture of metal hydrides.